Numbers. My group members are Andres Alvarez, Nathaniel Dixon, which is me, and Renaldo Bradford Hyacinth. So the definition of the law of large numbers in regard to number statistics is essentially defined as a theorem that shows that as the number of identically distributed, randomly generated variables increases, their sample mean approaches their theoretical mean. For example, if we try flipping a coin with one head and one tail, we would expect the probability of landing on heads or tails to be 0.5 for both. So, this theorem proves that the more we flip the coin, the closer the average of all the data would be to our theoretical mean, which is 0.5. And looking at the history of the law of large numbers, despite Girolamo Cardano, who was an important mathematician during the Renaissance, being the first to recognize the law, Jacob Bernoulli, a mathematician from Switzerland, proved it in his book Ars Conjectandi in 1713. This book, meaning the art of conjuring, contains many combinatorial topics and central ideas in probability theory. In this book, Bernoulli discovered the law of large numbers by playing a game that only has a win-loss chance with a high amount of repetitions. And after playing it, he found that as the number of repetitions of the game increases indefinitely, the fraction of times the game would be won becomes closer and closer to the expected probability of a win. So we can now look at an example of that proof. Again, let's imagine we're playing heads or tails, and as we've seen before, the probability of getting a heads is 0.5, and a tails is also 0.5. So let's set the probability of a heads to p equal to 0.5. If we were to play around 5 games, it is likely that the number of heads that we landed compared to tails isn't close to 0.5. So this is where the idea of large numbers comes into play. Bernoulli proved that the more we play the same heads or tails game, the closer the heads to tail ratio would be to p, showing the importance of repetitions when trying probability-based games or trials. And looking at the relevance of this same law in today's world, not too surprisingly, it can be put into practice in many, many different ways of society. And it also mostly applies to areas where money or economic value is present. Moreover, the same law can also be used to optimize sample sizes and rough calculations that would normally be difficult to analyze within trials and experiments. So we can now take a look at the different applications of the law and its usefulness during today's society. First, we can look at casinos, and this law of large numbers is utilized by casinos in order to maximize profit. And looking at the chances, the casino itself wins slightly more than half the time, around 51 to 56%, which also means that the casino guests win less than half the time with their luck. But no matter how many guests attend the casino, it doesn't really affect their win percentage. So, for example, I can play some games and win, let's say, $100, and Andres can play and win $50, but Renaldo can play and lose $200. This may seem off track, but point of the matter is some will win and some will lose, but the ways in which the slot machines are designed are meant for the casino to always financially win in the end, regardless of the population that attends the casino. And looking at renewable energy, if you don't understand how renewable energy works, solar panels and wind turbines both produce electricity from natural resources, the sun and the wind, respectively, that travel to generators that are then stored. The issue falls is that it isn't always windy and definitely isn't always sunny, so renewable energy isn't always able to be utilized. So, how do companies optimize their energy? They actually connect thousands and thousands of solar panels and wind turbines to a single power grid, which ultimately increases the likelihood of enough renewable energy being stored in the grid. And to note as well, increasing the number of turbines and panels used greatly helps workers anticipate the amount of renewable energy that will be created, since it allows them to note the expected average among the thousands of machinery. And now, Renaldo will be presenting his part of the project.
Large number says that if we toss a coin many times, the number of heads will be approximately the same as the number of tails. But we cannot say this definitively. It only tells us that the heads is very, very close to the number of tails, but not that they are equal. And we are about to go in depth into a theorem. We're going to prove a theorem about the simplest form of the law of large numbers. So suppose that we have t, where t is greater than or equal to 0, and t is less than or equal to m. So the probability that out of 2m independent coin tosses, the amount of heads is less than m minus t, or greater than m plus t, is at most m divided by t squared. So let's talk about this for a little bit. If t is less than the square root of m, then this pretty much means nothing, because we know that the probability of anything is at most 100%, and the upper bound that is given is greater than 100%. So that really doesn't do anything for us. But if we choose, let's say t to be 10 times the square root of m, then we can get something interesting. So with the probability of at least 99%, the amount of heads among 2m independent coin tosses is between m minus 10 times the square root of m and m plus 10 times the square root of m. Of course, m needs to be greater than 10 times the square root of m, or m needs to be greater than 100, so that it's have any meaning. But we're talking about the law of large numbers. So if m is very, very large, then 10 times the square root of m is much, much smaller than m. So the heads is going to be very close to m. Okay, let's give an example. So suppose that we have m is equal to 1 million. And so 10 times the square root of m will be equal to m divided by 100. So the probability is going to be at least 99%, and the number of heads is going to be within 1% of m equals n divided by 2. Yeah. So let us go and suppose that we have event a sub k, and a sub k is the event where we toss exactly k amount of heads. So a sub k is mutually exclusive. So for every outcome of this experiment, there will be one a sub k. The number of outcomes for a sub k is the number of sequences of length n, which has k heads and n minus k tails. So if we go into specific detail about which n are heads, we can pretty much prove this. And we can do this using combinatorics. N choose k ways. So a sub k has n choose k elements. And we know the total is going to be 2 to the n. So we can get the following, which is on screen. Probability a sub k equals n choose k divided by 2 to the n. Okay. But what about if the probability of the heads is far from the expected number, which is m, where m is equal to n divided by 2? Say it's less than m minus t or greater than m plus t, and t is any integer that's positive and greater than m. So if we refer to figure B and plug in our numbers, we can see that the probability that this happens is going to be figure C. 1 divided by 2 to the 2m times 2m choose 0 plus 2m choose 1 all the way to 2m choose 2m. Yeah. And if we apply theorem A, which is on screen, then and we let k be equal to if we apply theorem A and we let k be equal to t squared divided by m, then we can get figure D, which is 2m choose 0 plus 2m choose 1 all the way to 2m choose m minus t minus 1, which will be less than m divided by 2t squared times 2 to the 2m. Yeah. And since we have the symmetry of the Pascal's triangle, we can go on to the final figure, figure E, where 2m choose m plus t plus 1, etc., all the way to 2m choose 2m is less than m divided by 2t squared times 2 to the 2m. So this is the probability, and we found that the probability that we can get either m minus t or more than m plus t heads is less than m divided by t squared. And we've essentially proven this theorem, and we've basically shown that the law of large numbers is not like anything insane, but it's simply the properties of binomial coefficients.
Hello, my name is Andres Alvarez, and today I will be presenting the differences between the weak law of large numbers and the strong law of large numbers. As we can see, the strong law of large numbers is considered to be stronger because it is equivalent to equation 1. On the other hand, the weak law is weaker because it is equivalent to equation 2. Now, what does this mean? The notation might be tricky to understand, but equation 1 means the limit as n approaches infinity of the absolute value of Sn over n minus mu is equal to 0. Now, this is supposedly considered stronger because the strong law of large numbers has a probability of 1, whereas the weak law does not. The weak law of large numbers is weaker because of that significant reason. As we continue on to the next slide, we can see other key differences. I wanted to point out that the most important differences would be that the weak law of large numbers requires that the convergence be in probability, whereas the convergence of the strong law of large numbers requires it to be almost surely. Now, continuing on to the differences, we say that the strong law has a probability of equal to 1, which is quite important. Also, the strong law of large numbers proof is much more complex than the weak law of large numbers. However, the proof for the weak law of large numbers can be done using two methods. The proof by Chebyshev's inequality assuming finite variance, and then proof by the convergence of characteristic functions. Now, all these notations and definitions are quite confusing, but we can break it down to something much more simple for us to understand. In the weak law of large numbers, if we have a large sample number, there is a very high probability that this will reach close to the expected value. Now, what does this mean? This means that there's a weak convergence. This might be misleading because it is not like weak, but in the terms of the strong law and weak law, it is considered weak compared to the strong law. We can say for the strong law of large numbers, if there is a large sample, that the strong law of large number will almost surely be close to the expected value. We note this as a strong convergence, and this allows for the strong law of large numbers to be stronger than the weak law. We previously said that the proof is more complex. That is true. The proof is more complex and requires more to prove in the law itself to make sure that it is stronger than the weak law of large numbers. In the next two slides, we will be illustrating the differences between both laws. As noted in the weak law graph, on the left-hand side is what we saw, Sn over n, and on the bottom is n. We note that as n increases on the bottom, the random numbers or variables start to filter out and become more stable. The first part of the graph, or the left part of the graph, you see the values increasing and decreasing sporadically, but as we continue towards n, they become more streamlined, and we see where the expected value should fall, or at least the range of the expected value. It is important to note that in this graph and under the weak law of large numbers, the probability cannot be certain that these values will fall under this range, unlike the strong law of large numbers. Now, on the other hand, as we see in the next slide, the strong law graph, the strong law of large numbers, the left side has S of n over n, and then the bottom has n. There's this little interval between the values on the graph that we can for sure say that there is a strong probability, actually there's a probability of 1 equal to 1, that between these intervals that there will be a value located between these intervals. This is what makes the strong law of large numbers stronger than the weak law of large numbers, and that's why it's important to understand differences